Okay. So, circuit changes, last set of notes for circuits in general. So this one is, most of the stuff I've already alluded to or mentioned, but this is a little bit more specific and concrete. So we talked about like simple circuits, which are just like series and parallel circuits. So a complex circuit is anything that's, well, a combination of those. So oftentimes, more complex circuits can be analyzed by following these steps. Right? So if you have a more complex circuit, like I don't know how to do this, you go, okay, first thing you want to do is draw a circuit diagram. So if you don't have one, definitely draw one. If they give you one, that's useful, but you may want to just redraw it like on your paper so you can write stuff on it. You want to label all known and unknown quantities. So that includes current, voltages, resistances, capacitances, stuff like that. I would do that, if you really have no clue, just write down everything that you know and everything you don't know. That doesn't mean you need to find everything, but that way in your mind you'll know, okay, I know this or I don't know that, and it will lead you to, the next couple of steps. So then step by step, reduce the circuit to the smallest possible number of equivalent resistors, okay? So what you can do is when you have, and we'll go through these steps here in a second, it's like if you have a bunch of things that are in series and parallel, we'll kind of go to one area where you can see, okay, these two are definitely in parallel with each other, or they're definitely in series with each other, and with nothing else, okay? Well, if they're in parallel with each other, well, you know the rule how to reduce parallel things, right? So combine that into one resistor or capacitor, whatever. And then, okay, now that this is just one thing, how does it look with the thing next to it? Well, maybe now they're in series, but those are in parallel. And you can start to use your rules. And so the thing is like if you have things that are in parallel, use the parallel rule of Adam. If you have things that are in series, use the series rule of Adam. And so you can kind of like work your way back. And so there can be really complicated circuits, if we're talking just resistors, that you could essentially just reduce down to one resistor. And when you do that, then you go, okay, well now it's a very simple thing. I just have a battery resistor and I can analyze it. And so down to the smallest possible number. It's not always capable of going down to one. It just kind of depends. And then determine the current and potential difference across the equivalent resistors. Then you go back and you rebuild it out to this whole circuit, going along with your rules. You go, okay, well this part's in series. This next part I'm putting together is in series. So the current, which I already know, remains the same through all these, so I can find my voltage drops across these equivalent resistors. Then you go, okay, for this particular equivalent resistor, now it's actually, three resistors in parallel. So then you go, okay, well, the current's going to change when it's in parallel, but I know the voltage drop, so all of them keep that same voltage. So I'm going to find the current across the resistor, and then you work it back that way. So yeah. So use two important checks as you rebuild the circuit. Verify that the sum of the potential differences across series resistors matches the potential voltage drop for the equivalent resistor. And then verify the sum of the currents through parallel resistors matches the current for the equivalent resistor. So these things will make a little bit more sense as we do an example. Okay, so initially the switch in the figure is open. Bulbs A and B are equally bright, and bulb C is not glowing. What happens to the brightness of A and B when the switch is closed, and how does the brightness of C compare to that of A and B? Assume all bulbs are identical. Okay, so what I'm going to do here is I'm going to take this circuit and I'm going to work it with some of those rules. Okay, this is about as simple as a complex circuit can get. And so in order to work with these rules, I think it might be helpful to throw some numbers in there at first to help see what's going on. So it says that we have a battery voltage here and we have bulbs. It doesn't say the resistance of those things are, but it says that they're identical. Okay. So I'm just going to make up a resistance for these. So let's say that they have a resistance of 3 ohms. Okay. So we got 3 ohms, 3 ohms, 3 ohms. Okay. And we'll make up a battery voltage. I'm going to go to 12 volts and 3 ohms. Hopefully that'll help our math. Okay. So at first, this switch is open. so we can find the current through the whole circuit. We know our voltage, we know our resistance, so how do we find current? Ohm's law, so the current coming out of the battery is 12 divided by 6, which is 2. Everybody okay so far? So this current is 2 ohms, right? Now, for this first particular thing, that's basically it. Okay, there's nothing more complicated, because it was just one thing. So now, we know this thing has a current of, I see 2 volts, 2 amps. Okay. And that's going to flow through each of these bulbs. So now you go, okay. So what we're doing here is I'm trying to do the simple rules that it said here. So now I assumed it was one resistor, right? So now I'm working my way back to having 2 resistors, okay? Well, each one has 3 ohms of resistance, but the current is the same, right? Because they're in series. And since the current is the same, this one has 3 ohms of resistance, that one has 3 ohms of resistance. I can figure out how much voltage is dropped across each one by using Ohm's law, V equals IR. So what's 2 times 3? 6. So that means I'm going to drop 6 volts here, and then 2 times 3 again is 6 volts here. And so that's what the last slide was mentioning, is to double check. Well, what's 6 plus 6? 12, which is the voltage dropped across that whole particular equivalent resistor. And so we can check ourselves like that. Does that make sense? Okay, so that doesn't actually solve this problem, but that's just an example of some of those rules. So now let's throw in C, okay? So what I'm going to do here is I'm just going to write in a different color. The things will be a little different, right? So now we throw in C, we close the switch. Right, so now current is flowing here. So how does this change our circuit? Well, what are B and C now? And they're parallel, but they're in series with A. So we got to do, so again, in order to reduce this, you got to go to some, because you can't just add these 2 guys in series because they're not in series. This thing's in series with both of these. So we can pretend like both of these are one resistor, then we can add it in series to that. Does that make sense? So, in order to pretend like this is one resistor, well, we got to add them like they're in parallel. So how do we add in parallel? Add by inverse, so you got 1 over 3 plus 1 over 3, which gives me 2 over 3. So I flip that over and I get 3 over 2. Right? 1/2. So this whole thing here acts like one resistor that's 1.5, right? Now this 1.5 is in series with the 6, or with A, that way. So now I do 3 plus 1.5, and this whole thing acts like one resistor doing what? Well, 3 plus 1.5. 4.5. Okay, so now I'm back to kind of how I was before. I've just reduced this whole thing to one equivalent resistance, okay? So now again, it's still 12 volts. So 12 volts with 4.5 ohms. So can I find the current now that's passing from the battery? So I use Ohm's law again. I'll write up here. I equals V over R. It's not going to be pretty anymore. So what's 12 divided by 4.5? All these electronics. Do it manually. 2.67, and that would be amps, right? So now you'll notice here that this is more current than we had before. Does that make sense? Well, yes, because before our equivalent resistance was 6, and now it's 4.5. Which would make sense because we added one in parallel, which would reduce this guy's resistance, in this case by half. So we should flow more current. Okay, that makes sense. Okay, so now this is the current flowing through this little made-up circuit. So now let's expand it back and find out everything else. Okay. So now this current is going to flow through this first bulb. This is in series, so does this current change? No. So the current through this bulb is 2.67 amps, right? So this is flowing right here. And gonna continue to this point, right? Then we have the junction, so we'll deal with that in a second. So it's 2.67 amps, and we know that the resistance is 3 ohms. So we can use that to calculate the voltage. So now, for the second circuit, what's the voltage drop here? So I times R was 3 times 2.67. 11 times 3 is 8.01. You said 8.01? Yes. So about 8 volts is dropped on this volt. Okay? So now the current's going to hit this point and it's going to split. Right? Between our two parts of our circuit, I'll call it I1 and I2. So that's I total or whatever. So the problem is I don't know how much is going to go each branch. Now, in this case, they are the same resistance, but let's pretend like they're different resistances for the sake of argument. Okay, I don't know how much current is going to go down each branch. So the total current is going to be 2.67. So if you didn't know this, I mean, we do know it, and honestly, this is going to split in half, right? But even if you didn't know that, but if you knew like this one was twice the resistance of that one, well, then the other one's going to get twice the current, the first, right? Because more current is going to flow down the path of least resistance. But let's pretend like we don't know anything. How do we figure out the current? Well, the current's going to be based on the voltage drop, right? Because this whole thing acts like a 1.5 ohm resistor at this point, right? How many volts have I lost? 8. Now in this case, what's 12 minus 8? 4. What is the voltage of this side? If this side has a voltage of 12, 0. So this whole thing is 0. Y'all see that? So at this point, once we've dropped that voltage, this part has a voltage of how much? That's 8 minus 12. 4. So the voltage here is 12 until you get to the light bulb. Then it's 4, then it's 0. So what is the voltage drop on this part of the circuit? 4. Okay? Because this is parallel, so the voltage stays the same for everything. So the current device. Voltage is the same. Now, if we didn't know that, I mean, in this case, we knew this was 0. But if there was another part of the circuit here, we wouldn't be able to be like, oh, it's 4 or whatever. We do know the current is 2.67, and we know our equivalent resistance here is 1.5. So what is V times that I? 2.67 and 1.5. I know the answer. 4.605. So that's basically 4, right? Now, it didn't come out exactly 4 because, well, that 2.67 is a little rounded. But that should be 4 volts because of what we just said. But even if you don't know what it is, you know that this much current has to pass through somehow both of these sides, but in the end it acts like this one equivalent resistance. So now I know my voltage drop is 4 volts, right? So now I can split back into each individual one. And if I wanted to find the current here, well, that's the calculation here. Current is voltage divided by resistance. So each individual resistance is 3 ohms, and the voltage is 4. So it's 4 divided by 3. 1.33. So it's almost like this thing got split in half. Just what we said was going to happen. Because the current is going to come here, this 2.67 is going to come here and split. In this case, since they're the same size, it'll split even.
Hey, Mr. Dupree,
What's up?
would you like an Easter egg?
Sure.
You want me to put one on here for you?
Sure.
Okay.
You don't have Perry wearing these?
Actually, yes, he's in the hallway. But have a great break.
All right, so that's the current that splits between the branches, and then it's going to obviously have to add back up to give you your total out here. So analyzed everything literally to death. This is a small circuit. So here we can see that in the original circuit, it flowed 2 amps of current from the battery. And with our change now, it flows 2.67 amps. Right? Yes? Yeah. Okay. So let's actually answer this question. I just analyzed that to death, just for the sake of the rules. Initially, the switch in the figure is open. The bulbs are equally bright, because they have the same current, same voltage drop across them, which is what we found earlier, right? They both had 6 volts drop across them with the same current. Because power is your brightness, essentially. So it's I times R. Sorry. I times V. So they both had 6 volts, they both had 2 amps, so 6 times 2 is 12. They would both be using 12 watts of power in the first circuit. So I'm going to kind of write that off to the side here. So the power of the first circuit for each bulb was 12 watts. Okay, I'll call it circuit 1. Okay. So then it says, now what happens to the brightness of A and B when the switch is closed? Okay, well when the switch is closed, what happens to the current flowing through the first bulb? It's 2.67. It's more, and what happens to the voltage for the first bulb? It goes from 6 to 8. Well, if I did 2.67 times 8, is that going to be more or less than 2 times 6? More. So A's brightness should increase. Does that make sense? Because the current flowing through it increased. Okay. But what about B? Well, B originally had 6 volts and 2 amps of current, right? But now it has 4 volts with just 1.33 amps of current. They're going to go up or down? Down. So B goes down. So more current flows through A, but less current flows through B. Okay? Everybody okay with that? And then how does the brightness of C then compare to A and B? Well, C is going to have how much voltage? Yeah, same as B. And what about its current? Also the same as B. So how does C compare to A and B? Same as B. Equal B for less than? Okay. Now, could you have done this without any of the numbers? Possible. This is kind of up to you. But here, I think we went a little overkill. But that's essentially how the rules work, is when you have a complicated circuit, you want to try to get it down to the fewest number of components as possible, then analyze those, and then you can work your way back to the original circuit. And again, you should be able to check yourself along the way. Like we said, we used 8 volts here, right? We used 8 volts here, and we used 4 volts here. Well, what's 8 plus 4? 12, which is our total voltage. So in any circuit, all of the voltage is always going to be used, okay? Because it doesn't make sense, like when I started studying circuits, the teacher would say that, and that didn't make any sense to me. I'm like, but the bulb doesn't need that much voltage. Think of it like a cliff. If you push something off a cliff, and it only needs to fall 12 feet, but there's 100 feet to fall down, it's going to fall down the 100 feet whether you want it to or not. Okay? So when it comes to circuits, if you don't want this particular thing to have 12 volts, well, don't give it 12 volts. Because it's going to use all the voltage, right? Regardless if you, because basically if it's too much, it's just going to break. Like I said, just think about like pushing it off a cliff. Like if that's too high, then it's just going to get broken. All right. So like I said, we kind of analyzed that one to death. So here, I'm not going to do that there. Talk about this. Blah, blah, blah. This is essentially what we just did with that one. So the current's greater, blah, blah. So you have the same brightness too. Okay. Capacitor. So which capacitor discharges more quickly after the switch is closed? So here we have 2 capacitors that were charged somehow. Doesn't say how, just they're charged now. And it says, okay, which capacitor discharges more quickly after the switch is closed? So it's a little hard to look at because you go, okay, I got 6 microfarads on the first one and 5 on the second one. So with a smaller capacitance, it would probably be, probably have less charge on it with the same given voltage. And if that's true, the problem is this has a higher resistance, right? And that one has a smaller resistance. So a higher resistance, the current's going to flow not as fast. So in this case, A will discharge the quickest because it has the least resistance. The simple version is if there is no resistance, basically the capacitor discharges instantaneously. That's physically impossible. So, like basically if I just connected one into the other, it's not going to be instantaneous, but it will be based on like the resistance of the wires, which is going to be incredibly low. And so that's really the only thing slowing down your charge is whatever your resistance is. Does that make sense? So the resistance dominates in terms of discharging how fast it's going down. All right, RC circuits. This is the real last chunk here. And for you guys, we're going to keep it simple. Okay, this ain't physics thing. Because here's the problem. Capacitors, resistors are fun, right? You got Ohm's law and you're good to go. Capacitors are not fine because as you're pushing charge onto the plates, you know, the charge isn't flowing through like a resistor. The charge builds up. Because the charge builds up, you know, like, again, if you put 10 negative charges on this plate and you want to put another one, well, the charges that are there are going to resist the next charge coming in, right? So as it gets more and more charged, it's going to have more and more resistance to you putting more charges into it. So capacitors change with time. Okay, we're not going to do any of that fun calculus stuff with them. We're just going to say, okay, they change with time. So you have different scenarios, like they're either going to be completely discharged or completely charged, and sometimes we'll talk about how long it takes to charge, but we're not going to have a function that changes with time. Does that make sense? So it keeps it kind of easy. So an RC circuit is a circuit that contains a resistor and a capacitor. And so pretty much, if you just have a capacitor by itself, it is an RC circuit, with the R being the resistance of the wires. Because you always have wires, so there will always be some resistance. So in an RC circuit, the current varies with time, and the values of the resistance and the capacitance in an RC circuit determine the time it takes the capacitor to charge or discharge. Okay? So here we go. The figure shows an RC circuit consisting of a charged capacitor, an open switch, and a resistor before the switch closes. The switch will close at t equals times 0. Okay? So this is before the switch closes. So we have some charge on the capacitor. So theoretically, it's completely charged to whatever its capacitance is, 5 microfarads or whatever it is. And so we know for a capacitor, V equals Q over C. Right? In this case, it says the charge is Q naught. Why do you think it says Q naught? Yeah, the initial, because it's going to change the time. It will start, Q naught, and eventually go to 0 charge at some point. So we close the switch. So immediately after the switch closes, the charge will start to rush through the circuit. So we said the current flows from positive to negative. In reality, the electrons go from negative to positive. Right? So you can imagine as soon as you close the switch, the electrons will start to flow until this charge cancels out both poles. Okay? So the initial potential difference is V. We call it V naught, which is whatever the initial charge is divided by the capacitance. Whatever that happens to be. So the initial current, the rate at which the capacitor begins to discharge is going to be equal to I equals V over R, which is essentially Ohm's law here. You'll see this case, it's specifically saying the voltage of the capacitor, right? And more specifically, it's the initial voltage of the capacitor. Okay? So this is our initial current. So whatever that voltage is initially, divided by the resistance, determines the initial current that gets dumped out of that. And depending on your charge, I mean greatly depending on your charge, this current could be very high, right? Especially if your resistance is low. It's one of the reasons why we use capacitors. Sometimes you want a lot of current to dump at the same time. All right? So I don't think any of this is terribly shocking. Okay, so the current and the capacitor voltage decay to zero after the switch closes, but not linearly, right? This is not a line. So what happens is, it says, okay, you're going along, there's no current, right? Then at t equals zero, whenever you decide to close that switch, the current immediately jumps up to this number, whatever it is, the voltage divided by the resistance, and it will decay over time. Okay? The voltage on the capacitor, well, is whatever it is initially, which also decays over time. Okay? Make sense? And if you realize that the voltage is decreasing with time because it has less charge, that makes sense why the current also decreases with time. But at some point, it will theoretically eventually reach zero. The decays of voltage and current are exponential decays. So this is the actual formula for these curves. You may want to write them down. It's not like, they're not going to try to trick you on this or anything, but like it's not like a nice, what do you call it? It's not like a 1 over R decay or something like that. This is, you guys know this E function here, right? It's like a first grade. Yes, it's elementary charge. Good guess, Ron. So these are the two curves, and so notice that we have I naught and V naught in there, and so it ends up being E equals, or E raised to the negative T over RC. So here's the thing, like we're not deriving the formula, so this was physics C. I would take some time to show you guys where this thing comes from, but we don't have A, the time, but B, I'm going to assume that y'all are not, most of y'all are not super into calculus. So we're just going to pass by that. Okay? So an easy guess would be that they literally just guessed this. Now, what's interesting here is that you have the RC. So, in truth, go back here. This circuit here. RC is what we call our time constant, which we just saw in this function, so we'll go back to in a second. If you do the resistance of the circuit times the capacitance of the circuit, you'll get a time constant. It's directly related to how long it takes to decay. Okay? So what is the time constant for the top circuit? It's just R times C. Okay, now if you're looking at these, yeah, we should take into account units. But here's the deal, we have ohms and we have microfarads. So whatever it is, it's going to be something with micro in it. But what's 6 times 2? What's 5 times 3? This one takes less time. Now, does it take 12 seconds and 15 seconds? No. But you can kind of think of it like that. Like, oh, okay, 6 times 2 is 12, which is less than 15, so this one will decay faster. Make sense? If that is RC, that is your time constant. And the time constant is right here on the bottom of this. All right? So I'm not going to explain too much of this formula, other than it makes that graph that we just saw. So the time constant, tau, is a characteristic time for a circuit. A long time constant implies slow decay. terms of the time constant, the current and the voltage equations end up looking like that. So it's the same thing, just with a time constant in there. So instead of having RC, but this is what's really fun, is if you actually keep up with the units, like ohms are just a weird unit. It's like resistance, like if you think about like Ohm's law, like V equals IR, you solve it for R, it's V over R. So like ohms should be volts per amp. And if you remember, like volts are like energy divided by coulombs of charge, and current is coulomb of charge divided by, I'll just write this stuff up. I feel like this is on that thing. So resistance is current over, no, voltage over current. Right? Oh my gosh. One day. So this would be volts over amps, right? And volts are joules per coulombs, right? And amps are coulombs per second. So those cancel. So resistance is joules per second, is that right? Yeah, I did that right. And then you have capacitance. Oh yeah, because that's I was like, that can't be right. Joules constant. Like good. Because this is on the bottom of the bracket, right? Joules times joules seconds, that makes more sense. And so capacitance is so voltage is charge over coulomb, sorry, coulombs. Hang on. That makes more sense, because I remember it being real nasty. So, joules divided by coulombs. That's what that is. Joules over coulombs, right? So it's energy per unit charge times current is coulombs per second. Right, coulombs. So coulombs per second, so we flip that over, that'd be seconds per coulomb, right? Alright. Capacitance, on the other hand, so V is Q over C, right? So C would be Q over V. So Q is just charge, right? And V we just discussed is joules per second. So instead of screwing this up, I'm just going to go ahead and multiply it. So doing joules per coulomb is coulombs over joules. Yes? So multiply instead of divide. So then I should get C squared over joules. And so if I multiply R times C, R is joules seconds per coulomb squared times C, which is coulomb squared per joule. What do you get? Seconds. So it seems kind of strange at first that like RC would be a time constant, but if you're just following along with all those units, it is time. Which is why the exponent has to have a time in it, because you can't have a unit on your natural log your exponential function here. Because here, you see this is like I equals I naught. So I and I should have the same units. Right? There shouldn't be anything else on there. This is like V and V, so again, no units. So hopefully that makes sense, right? Yay. After I screwed up like that. Okay. So, the current and the voltage circuit do not drop to zero after one time constant, so that would be too simple. Each increase in time by one time constant causes the voltage and current to decrease by a factor of e to the negative 1, because t would be 1. So, and that would equal 0.37. 0.37. So, for the first first time constant, you're gonna lose about 37% of your current or voltage. After two time constants, not another 37%. So the time constant has the form RC. A large resistance opposes the flow of charge, so increasing R increases the decay time, and a larger capacitance stores more charge, so increasing C increases the decay time. So both of these things will make it take longer. Does that make sense? So more resistance, it decays slower. More charge in the first place, it decays slower. So here, the potential difference has decreased to 37% of its initial value. So whatever this initial was, you're down to 37%. But after two time constants, you're not down by another, you're to 37% of what was there already. Make sense? Or 63% loss. Does that help? So you lose 63% to here, then you're going to lose another 63% of whatever it was, and so on and so forth. And theoretically, it never reaches zero, so this should be very similar to half that we talked about. That theoretically, it never reaches zero, but in reality, it definitely does reach zero at some point. Okay. So the charging is similar to discharge. So here we just started with something and we let it go. So charging is similar to that. In other words, you should expect that same natural function in there. So charging is similar. Discharge, the current starts at a maximum and it decays to zero. So current is actually very similar. But again, not linearly. And the voltage across the capacitor is different because it starts at zero and increases to the max. Alright, so the time constant is still RC. So voltage starts at zero and increases to its max. So the voltage across the capacitor, because it should start with zero voltage. But current will still start at its max and decay to zero. Okay? And so notice here, like on these graphs, again, after one time constant, you're going to gain 63%, whereas the other one you lost 63%, or still have 37% left, however you want to say. And so here with our time constants, it's charging up. Here it's decaying off with our current. Notice that the current in the original one was, like the initial current for the discharge was the voltage on the capacitor divided by the resistance of the circuit. Here, it's the voltage of the source, that's what VS means in the graph, divided by the resistance of the circuit. Okay. So to me, it's very similar. And again, after one time constant, you're down to 37% of whatever you originally had and so on and so forth. One of the things that you can see on these graphs, I really like these graphs. I couldn't find graphs like this in the other set. Is that basically 5 time constants is where we say it's done. Okay. Whereas like for half-life, we say it's done after 10 time constants. Or not radioactive. Yeah. So here you'll notice that the function for current is exactly the same. Does that make sense? The difference with this function of current is the I naught is calculated differently because it's the voltage of the source as opposed to the voltage of the capacitor. And then your discharge is, what is this guy? What is that? What is this epsilon? What is this guy here? This. That's the EMF of your source, the voltage source. That. Does that make sense? Like this is the voltage of the battery. Are you okay with that? So this is not the, like in the other function, V naught was the voltage of the capacitor. This is the voltage of the battery that's charging the capacitor. Make sense? But now, instead of it being just e to the negative t over RC, it's 1 minus e to the negative t over RC. Well, because it's a charge curve versus discharge. So if it was e to the negative t over RC, it would be doing this, but the voltage is building up, so we want the opposite of that, so we do 1 minus that. Because eventually this thing will build up to being 1 at some point, like as this gets bigger here, eventually e to this negative function here will become 1, so you have 1 minus 1, which will be, no, that's what I just said. Because what's 1 minus 1? 0, okay. But if you have 0, that's your initial voltage on the capacitor, right? So at first, this thing is basically 1. And so as this thing gets bigger and bigger and bigger here, this thing will eventually decay to 0. Right? That will decay to 0. So once this is 0, this will be 1 minus 0, which is just a voltage. That's simple. Make sense? The following circuits contain capacitors that are charged at 5 volts. They all were charged at 5 volts. All the switches are closed at the same time. After 1 second has passed, which capacitor is charged to the highest voltage? So if you think about that function, I'll let you know. Okay. All right, what's all that? See? So, why? Okay, it's slow. Okay. Like 1 times 2 is 2. 0.47 times 2 is 1, or less than 1. 1 times 3 is 3. And 0.47 times 3 is like what, 1.5 or something, so. Yeah. Okay, slow, easy. Right? In the following circuit, the switch is initially closed, and the bulb glows brightly. When the switch is open, what happens to the brightness of the bulb? So, initially the switch is closed, which means current will run through the bulb. What's going to happen with this? If this is closed, well, current will go through here, over there, right? So when the switch is closed, will any current run through this capacitor? No, it has no reason to. Okay. So initially, this thing acts like it doesn't have a capacitor in there at all. Right? So now you open the switch, now the current has to go through the capacitor. What's going to happen to the bulb? Agreed? Agreed? You guys still thinking? Because when you close the switch, it's not going to change the resistance of the switch. But now the current's going to flow through here. And so initially, the current flowing through the capacitor will really just depend on that. Right? It'll be the voltage of this thing divided by that. That'll be the current, which is what it's currently doing. But over time, this capacitor will build up charge, and as it builds up charge, it will slow down the current and eventually stop. So it'll start with the same brightness and then get different. So the red C and D, I think those are pretty obvious, but C and D charges faster than C, but then ends up with less charge than C, which would be less than the original charge. And then C charges the slowest, but charge to, it still seems to be going up. C might eventually get the same charge that you originally had. So, all we're doing is we're changing the value of the resistor, making it small. So how does that change your curve? Well, B. So a smaller time constant, because R went down, so RC would go down. So that means it will charge or discharge faster, right? So you should have a steeper curve, so both A and B are looking good in that respect. But is it going to change how much charge gets on the capacitor? No, you have to change the capacitance. Right. So same amount of charge. Okay. At the end. At the end. All right. Do y'all have any other questions? All right. Well, I'm going to go ahead